actually, this one is if you look at the group, and then they actually with the characters.
Sorry.
So this is not yet started.
No. It's live broadcast. Oh,
So,
sorry. Okay.
so in the normal system, maybe I discuss something general, but so maybe I just give you some outline of the construction, and then I discuss some of the ingredients. So in fact, now we consider here lambda 0, and then going to somewhere. This one is maybe again Lagrangian ring. But now this one is rather strange things. So this is a general story. I will explain what it is later, but now I just gives you the definition of this. So this one is maybe lambda of y1 so rather strange thing, and then take a quotient by and then take a closure with respect to this cycle. And so I haven't really explained this one. And I somehow mentioned the closure with respect to something. But anyway, I haven't really defined anything about the closure in this thing. But anyway, so right-hand side, we will define later, is something like this. And this side is actually quantum cohomology, which I also briefly discuss later. And moreover, actually here we put some little bit more decoration. So here I may put B here. Maybe I will explain what it is. And then I put B here. And I may put B here. And B is an element from this thing. And we denote this map by Ks B. And our main theorem is that this one is isomorphism. I haven't really defined the mapping. I just write something here, and then maybe you will see. So here, maybe you take some element from here. Maybe I take an element A here. And then I haven't really defined the potential function. I define potential function after bulk deformation, and this is actually bulk class. So anyway, so here I consider B, and then plus epsilon times A, and then differentiate with the epsilon, and then take its class in here. So this is a mapping we consider. And our theorem is, so x j omega is compact toric manifold. And then this one is actually a ring isomorphism. So in the morning, I discussed the isomorphism quantum cohomology with Bachelle's quantum cohomology ring. And you know the quantum cohomology is isomorphic with Bachelle's quantum cohomology in Fano case. And then the Bachelle's quantum cohomology can be also understood as a J-Cohen ring of potential functions. Therefore, you have something like this without this yellow one in Fano case. But here, actually, we want to understand that mapping more geometrically, or maybe in Floer theoretically. And this is the way to understand. So what is it? So B is what we call the bulk class. And so it's in fact a cohomology element from cohomology of this. And this is actually sum of C plus lambda plus. And our general story, non-toric case, only deal with this usually. But here actually we can also consider grand ring C. But anyway, so you have bulk class. And then we can deform our infinity operation by using this B. So this I will discuss later. And in this case, again, this H1 of LU of this lambda 0 is contained this Mallow-Cartan element of this LU, but after this bulk deformation. So we deform the whole story by this class B. And then because of this, we have a potential function, POB, LU, right? From this H1 of LU from lambda 0 to some lambda 0. So this is, again, potential function. And then from here, actually, we can also consider PO B of X. So here again, it's a kind of change of formal variable. Again, this yi is equal to y of u times t to the ui. So this is a function in variable y of u. And then you have some expression. And then you just plug in this yi in this potential function Lu. And then you get something which doesn't depend on u. And so this is our bulk deformed potential function of the toric manifold. So I explain this. So now I change the bulk class a little bit. And then each deformation we have some potential function. And then consider its infinitesimal change. Right? Just to consider the deformation of this interdistrict. And then take its equivalent class here. So this is a nothing. Okay. So maybe I just recall a little bit about this quantum cohomology, even after this bulk deformations. So maybe big quantum quantum cohomology. So this is just a general story. So let X omega be a closed-simplective manifold. Then you know the Gromfit invariant. So Gromfit invariant is a mapping from this H star of X. Maybe in our case, maybe I also take lambda 0 tensor, I don't know, L to this lambda 0. Okay, so maybe easier to work with this. So okay, so let A be a second cohomology class, right? And then we consider Gromfit invariant of genus 0. So maybe I denote by phi of A. It is actually a mapping from here, maybe L here, to this. So namely, we consider MA, its moduli of stable maps without boundary of genus 0. And sorry, maybe I just put L here and the L map point. Right? Representing class A. So you consider such a thing. And then we have a bunch of evaluation maps, right? So here I have an evaluation map, F1, FL, maybe mapping to X, X. So therefore, then if you take any element like C1, CL from this tensor product, L's tensor product of cohomology, and then we may just define this phi A of L of C1 CL is equal to just integral of this MA, integral of the class F1 star of C1 with FL star of CL. And in fact, instead of this integration, you may just consider just usual singular cohomology class, and then you put it back to this space, and then certainly you need to use some virtual technique in general, but then you just take its virtual fundamental class, and then just take a evaluation against virtual fundamental class, and you get this number. So this is the Gromfit invariant of genus 0. You can do the same thing for higher genus. But then maybe I just denote by phi of T. Yeah. So this is actually a sum. Maybe 1 over L factorial of phi A L of T T, so L times, and then multiply with the T to the power A of omega. And then here I take a sum over L and A. And then you get something. It converges as a formal power series in this T-adic topology. So again, in the element in the Novikov form. So this is actually an element in this lambda 0 stuff. Okay? And then if you consider, so T is actually a linear combination of this thing, right? Ti. I didn't really give the name. So Fy here, so let Fy be a basis, maybe a homogeneous basis of this cohomology. And then you just take this, and then you can consider the third derivative of this. Yeah, at the point t. And this is actually structure constant of the, maybe structure constant of the t deformed quantum cohomology. So what, in which sense? So this is actually like this. So you have this ddti, and then ddtj. So so ddti is actually element fi. So this is actually, you identified fi, and this one is fj, okay, as an element in cohomology. And then you consider this ddtk, and this is fk, and then you take this complete duality pairing, and this is this one. Okay. So Poincare duality pairing in ordinary cohomology sense, that this is actually non-degenerate, right? Poincare duality is non-degenerate. So therefore, yeah, this one, yeah, if you know the pairing with respect to each basis element, and then certainly you know this, right? So therefore, this one is defined by this formula. And then this one is actually gives you associative product. That is actually equivalent to say that this thing satisfies so-called WGBB equation, right? And so the proof of this actually just little analysis of the moduli space. And maybe if somebody enters in, then I can also tell this. So this is a story. But what does it mean, right? So here, this is very, very similar to the story I explained before, or in fact, we know this story, and then somehow we imitate this. So that is this. So we consider potential function of B and then take its derivative with respect to xi. And then what you get is this M1B of EI, right? So this may be better to use different letters, maybe AA and A. And different xi give you this. So we have this. So this is also sum of several terms coming from the iterated integral on the moduli space. And then just to take partial derivative risk to some direction, and then you get this. And here we also do the same thing. So this is such a sum, kind of generating series, and then take certain partial derivatives, and you get something. So, for instance, if you consider this phi of A of L and T, T, right? And then if you differentiate it in Ti direction, what do you have, right? So this one is equal to the sum of the following term. So I have to differentiate. I have to pick up one place. So then phi of A of L, and here maybe T is here, and then T is here. But here I differentiate in Ti, so therefore here I have Fi, and T here, T here, T here, T here, and then this is maybe a case place, and k may be from 1 to L, right? So anything. Now you want to differentiate again. Then this one is independent of t. So therefore, if we differentiate this one, then certainly 0. So therefore, you have to pick up one of the rest and then replace bold t by fj, right? And so on. So somehow, if you do this third derivative, then you have to pick up three places and then replace them by fy, fj, fk. And then you may get something. Sorry. I think yes. So the roughly this is a big quantum cohomology. So quantum cohomology somehow has a deformation parameterized by the cohomology class of X. You just do this. In other words, so the picture is like this. So usually maybe you may consider some small quantum cohomology. In this case, we consider a holomorphic sphere with 3 marked points. So here you have P1, and then you have 3 marked points. And then 3 marked points on P1, rigid object. You have unique modulus. And so you consider mapping to X. And then you pick 3 Poincare classes of C1, C2, C3. And then consider the mapping from here to here, which may hit these things, right? And then from here, you know the story for the quantum cohomology. Okay? But big one is maybe you have more marked points. I don't know, maybe n marked points. And then, so you have additional marked points several places. And then we are sure that they actually intersect with other things. So this is actually, in this case, maybe T plus. And so just to put additional mark points, so M is arbitrary, so M is anything. M is anything, like N. It runs over this. Consider everything, right? Then why we have this associativity? So associativity actually follows from here. Yeah? So usual case, we consider moduli space of P1 with 4 mark points. So this is actually moduli of genus 0 curve with 4 marked points. So then maybe in general we have just 1, 2, 3, 4. So just like this. But in some case, I may have, say, here 1 here, and then 2 here, and then maybe other component like this. So 2 components. And here I have 3 and 4. This is one. So we have this, and then if 3 and 4 are getting closer and closer compared to 1 and 2, and then you may have this picture. And if you consider another degeneration, like here is 1, and here I have another 1. Sorry, opposite one. I have another one. So here is 2, and here is 3, and here is 4. And then, so actually this moduli is complex 1-dimensional, right? So this is complex 1-dimensional. And this is 0-dimensional. and this is zero dimensional in the moduli. And so you just consider just a path from here to here. So this in fact, this moduli space is just P1 itself. And so these two correspond to certain specific point in P1s, and then you just join them through the path. And so I have here also M4 of A. So this is the moduli space of stable maps of genus 0 and 4 map points representing class A. And then you just forget the mapping, information of the mapping. And so forget the mapping. And contract unnecessary as an unstable component if there are. Yes. So if you just forget the mapping, if your domain is already stable, and then just keep that thing. But you may have unstable component in the domain, then you just contract it. So then you have a map from here to here. Okay? And then, so this one is actually same as P1. So you have a 2 points in P1, so therefore you just join them by a path, interval. And then consider, so here I have a path, maybe 0, 1, joining this one, right? And then over 0, you have a product. Yeah, you have a mapping from this and this. This is 1, 4, 2, 3 to x, such a thing. And over 1, I have a different one. Here is 1, and here is 2, and here 3 and 4, and the mapping to x, right? So such a kind of thing. And then using this and this kind of ideas, in this case, you first multiply first two entries by quantum multiplication, and then you just multiply with the fourth one, right? So like a C1, like a C1 and C2, and then C3, right? And if you have this, and then this is something like first I have a product of C2 and C3, and then multiply with this C1. And then you just consider this path. It gives you some cobordism. So therefore, you just consider the cardinality of such configurations, and then they must be the same. So therefore, these two are same. So this is actually kind of, yeah, maybe better to say this C3 and C4 Poincare duality, and this one is also C4, something like this. Okay, so this, maybe I 1, 2, 3, 4. So therefore, this numbering is not correct, but maybe you can just correct it. So this is the way to prove associativity. And if you have this, the story is almost the same. Story is almost the same. What we do is only this. I have a map from M4 plus M, right, to of A to M04. Okay? So this is first forget the last M map points and the map and contract an unstable component if there are. And then you have this. You just forget last M map points and then do this. Okay, so yes. And then we also consider this picture. But now we may have some mark points in this side. I don't know. Like this. So here I have a 5 mark points. So 5 mark point may be decomposed into 3 and 2, or maybe 1 and 4, or 0 and 5. Anyway, so you may just distribute your mark points on arbitrary ways, here and there, and then add them up. And so, exactly similar to this, not exactly, but similar to the previous argument, actually using this, actually you can also show the associativity of this product. So this is a basic proof verification of this WDBB equations. And so this is the quantum cohomology. And here you may wonder that these two things are really same or not, because here I just somehow treat the first 3 or 4 mark point special way, right? Here I just differentiate something arbitrarily. But it is okay because in this case we have kind of symmetry here. If you just switch factors, and then actually up to sign, I mean, if all the cohomology classes are even, certainly there are complete symmetry by symmetry group acting here. If there are some odd elements, then you need to take care of the grading of all the things. But anyway, you know that if you have a graded object and then you just permute them, then you have certain signs there. And so therefore, this one has such a symmetry. And then it doesn't matter whether you just differentiate this one or this one. And then here I have this one by L factorial. So therefore, working with this little bit, and then actually you can solve this. Okay, so this is a big quantum cohomology story. Okay. So I briefly discussed this quantum cohomology. So therefore, I also want to discuss a little bit about Seidel homomorphism. And in our argument, actually we just use the usual Seidel homomorphism. But certainly we can also be the form version of Seidel homomorphism. But anyway, this is just, I don't really use. Okay, so what is this? So x omega is maybe here closed simplex manifold. And let denote by Helm x omega be the group of Hamiltonian diffeomorphisms. I think at the beginning I actually remind you what it is. And then Seidel homomorphism is actually mapping from pi 1 over Ham to the element of quantum cohomology. But I need to take this maybe close here. That means it's the group of invertible element here. So this is actually a group of invertible elements in quantum cohomology. So Seidel actually noticed there is such a homomorphism. He constructed this. Okay, and in the toric case, I mean, at least the toric case, actually, McDuff and Tolman actually use this to interpret these quantum standard rational relations. So I just briefly discuss this. Okay, so let phi t, maybe phi t, a loop of Hamiltonian diffeomorphism. So in fact, yeah, just a looping Hamilton diffeomorphism group. And then from here, we want to cook up certain bundle over P1. Maybe I use this one so often, so I don't know. But it's, yeah, maybe okay. So just this. Okay. So this is the following. So P1. So this is S2. S2 is actually union of two copies of disks. And so here the boundary of D0 is identified with boundary of D1. And then here you consider this D0 times X. And here you have D1 times X. And this is a bundle over D0. And this is a bundle over D1. And then over here, you want to glue them together, right? So over here, I have a D0 cross X. Sorry, what's this? And here I have a D1 cross X. So therefore, we want to have this identification using this phi. So like, I don't know, maybe EI theta of X is mapped to EI theta of, sorry, EI, I don't know, E 2 pi square root minus 1 theta X, and here E 2 pi square root minus 1 of theta of phi theta X, something like this. Maybe it is negative. So here, actually, I consider one disk is here, and another disk is, I don't know how to say. This is actually, no, I don't know. If they are oriented disks, and then certainly the boundaries should be glued so that orientation reversed. And then here, I need to put minus sign here. But anyway, you know how, you want to have a bundle over P1 or S2, then you just decompose the base into two pieces and then just try to glue them together along the boundary. And so maybe you understand what it is. So from this loop of Hamilton diffeomorphism, you can just have this. And this is, if this is the case, then this P phi over P1 is so-called Hamiltonian fibration. So what does it mean? So certainly one way to understand it, a structure group is actually these Hamilton diffeomorphisms, but that is actually equivalent to say the following. So there is omega phi, which is a two form on this P phi, so that it has two properties. So d omega phi is equal to 0. So this omega phi is actually just a closed form. And secondly, if you restrict omega phi to the fiber, and then this is actually same as the original fiber. So you have fiber-wise, each fiber is identified with X, and ambiguity is just this Hamiltonian diffeomorphism. So therefore, the simplex form is actually preserved. So each fiber, you have a simplex form. And so each fiber, yeah, so you have this. But this one is extended to the global form on P phi, so that this is closed. So this is a Hamiltonian fibration property. And this is not really true for in general. I mean, if you just have a loop of symplectic diffeomorphism, it is not true. So I just give you some note. So if not if if we have a psi t, a loop of symplectic diffeomorphisms, then it may not be true. So the very easy example is just a torus. And so you consider this as torus, and so S1 times S1. And then you may just act S1 on the first factor by just rotation and fix the second factor. Maybe just consider such a thing, right? So like rotating this one, rotating this direction. And so here and this. So then this is actually a certainly symplectic diffeomorphism, right? Symplectic diffeomorphism or symplectic S1 action, but not Hamiltonian action, but not Hamiltonian. And if you consider this associated bundle of this p psi, then this part is fixed. So therefore, essentially, you consider this bundle, and that is actually just a hop bundle. So then this one is actually S3 cross S1, and then map to S3, and then here is a hop bundle here to S2. So this projection is a projection of P phi, right? So this. So the P psi is a bundle over S2, but the total space P psi is actually isomorphic to S2 equals S1, and this has no H2, so there's no way to extend this closed form, symplectic form on the fiber to this, because restriction is not converse to 0, right? So Hamiltonian condition is really necessary. So what I'm saying is here you have Hamiltonian diffeomorphisms. This is quite essential. Okay. So now you have this P phi over this P1. Then there is such a omega phi, but there is a so-called coupling form, right? So coupling form omega phi. So coupling form, certainly omega phi should satisfy this. So d of omega phi is equal to 0, and restriction of omega phi to each fiber is equal to omega, but also the following thing. So if you consider omega phi, and then take a top power, not top power. Maybe, top power. Yeah, top power. Okay, and then just take this piece loop, and this must be equal to 0. Yes. So here it may be just n or something. I think this is okay, right? No. N plus 1. No, n plus 1. So maybe it's top power. So then this. So for coupling form, actually, this class, the cohomology class of a coupling form, is so-called coupling class. Is well defined. So if you have a Hamiltonian fibration over S2, and then even not S2, you may just pick up some coupling form in that fixed class. Okay. Then we do the following. So I have here CP1 and P5 here. We can actually construct complex, almost complex here, so that the projection is holomorphic, and at each fiber, it is, maybe it is a almost complex structure on the M, compatible with omega. And now you may consider such a holomorphic sections of this. So you consider such a things. So now we consider the following. So this is M and section class of this P phi. And then again, we need yes. Okay. So there is one thing. So remark. So there is a section of this P phi. This one. So why such a thing is true? And this is actually a consequence of Arnold conjecture. It's a solution of. So that means any Hamilton diffeomorphism has a fixed point. But anyway, in the proof, actually, it says more. So you have a Hamilton diffeomorphism, and then you just consider this Hamiltonian isotopy. You follow the Hamilton isotopy, and then there appears some closed orbit, which is contractible. So in particular, this one has the contractible periodic orbit of Hamiltonian isotopy. May not be a loop, but in this case, we have a loop. Yeah, we have a loop. So at each point, you have phi t like x. It's a loop, already loop. It's a periodic orbit, right? But no conjecture, the solution and conjecture says that there must be a contractible one. So therefore, this one is actually a contractible loop. And then, if you look at this construction, right? So here, you may have just a constant section here, and then this side, constant section, is mapped to this orbit. But this orbit is contractible. So therefore, you can extend it to the section to the other side. Okay? So in this way, because of this, actually you can show the existence of cross section. So you have some section here. Then the sidal homomorphism may be defined the following way. So here you have maybe this 0 and infinity in CP1. And over here, we have this P phi, right? Something P phi. And here, I have a fiber like M0, X0, sorry. I have another fiber, X1. And then consider some section of this. Okay? So now we consider this sigma. Sigma may be a class in H2 of P phi of Z, which represents the sections. So so that sigma represents the section. Or sigma is represented by a section. Okay, sorry. Sigma is represented by a section. Okay, you have this. And then I denote it by, say, H to section class of P phi. Okay? And then for each sigma, we can consider the moduli space M of sigma, right? So this is a kind of moduli of holomorphic sections of this P phi P1 representing class sigma. Okay? And then we need to take its kind of compactification. Compactification, so maybe it's better to not only section, but kind of, I don't know, maybe kind of stable sections. That means you have some section. In addition to the section, you may have some holomorphic stuff in the fiber. So you have some P1 in the fiber, and then you have this section. Okay. So you have this. And then because this one is parameterized by this fixed domain, so therefore we have a map from F infinity, which is a map from M sigma to X, sorry, this is X infinity, sorry, X infinity. Okay? So I don't put any constraint on this fiber over X0. It can be moved anywhere. But then I take the evaluation at infinity. Right? So this is actually a cycle, at least in virtual sense. And so therefore this one gives you a class, some class in this H star of X infinity, maybe with rational coefficient. Okay? So if you take its Poincare dual class, and then you get something. So okay. So I don't know. So I didn't really give the name for the Seidel homomorphism. I don't know. Maybe Seidel homomorphism. So therefore S, and then this phi is equal to the sum of this Poincare dual class of this F infinity M sigma to X infinity, and then here this is a little bit interesting thing. So here I have T, and then integrate this coupling form over this sigma. And sometimes maybe you also want to put some E here. E is a parameter encoding the degrees. And then here maybe C1 of T to the vertical tangent bundle of P phi, evaluate with sigma. If you put this in, then grading is also somehow well defined. But anyway, if we forget this, and then this is just an element in ungraded things. But we have this numerical parameter. Okay, so this is a Seidel element. And maybe this I don't know, this kind of modification may be first introduced by McDuff. They're using this kind of coupling form. Maybe somebody else, but. And so then this one is actually an element in quantum cohomology. And why this is invertible element, and why this is the case? So yes. So now we consider the following. So here you may consider this here 0, and infinity here. Okay? And then along this loop, we use this phi t. Yeah? So 0 to 1. Yeah, so this loop here. But now we may also consider following thing. Maybe 0 is here, and infinity may be here. And maybe I just put something from here. And here I may take this phi. Okay? In other words, I may move this map point to somewhere else. Anyway, the bundles are actually isomorphic, right? Bundles are isomorphic. So it doesn't matter whether the way you cut it into two disks and then glue them back by phi, it doesn't matter, right? So you cut it here and then glue them by phi, or cut it here and then glue them. And then you get the same isomorphic total space, right? And now you consider further deformation of this. Like this. So over here, over here, it's actually now trivial. It's a product bundle, right? And so somehow you just do this degeneration of surface. I mean, in this case, actually, I have no moduli, so therefore it's a little bit strange. But somehow, yeah, you just consider this configuration, you just smoothen this, and you get this. So from here to here, this somehow smoothens the node. And this way, you degenerate somehow. So, okay. And then this is trivial. So it's a completely trivial, like a P1 times X. Over here, I have just a P1 times X. And then here I have P1 here, and then we may just consider this sort of things. But here, there is some non-trivial effect, right? So this one, so I don't put any constraint 0 here, but I just consider the image here, right? So if I consider section here and section here, and then section here, then it decomposes into section here and section here. They meet here. So therefore, this one is now just a mapping from P1. So therefore, I have here 0 and infinity, and then I pick this point here, right? Maybe 1. And then this one is just a holomorphic map to X, right? This is just a product and holomorphic map to X. And so here, the input is actually this S of phi. And here you have 0 here. So you put some element from here. Then this is nothing but a quantum cut product. So somehow we have the following. So here I consider quantum multiplication by this. And so this is a mapping from here to here. Right? So this one is actually now using this M of sigma, and then I have this F0 and F infinity, and here I have X0 and X infinity, and then I just pull back something and then push out like this. And that way we have this, but this one is same as this quantum cut product. Okay, so this kind of picture gives you this map, but this map is actually equal to the quantum multiplication side class. Okay, and then it is we also have the following. So this S of phi composed of psi is equal to S phi S psi. Yes. Because at the beginning, you may have here phi composed with psi, and here 0 and infinity. But this one is somehow decomposed into these things, right? So maybe I don't know how I write it. So here I have phi, and 0 and infinity, and then maybe here I have another one here, and then maybe this one is psi. Yes. So if you have sphere, and then here you have phi, and here you have another psi, and then this is actually homotopic to this phi psi, right? So using the clustering function phi along this, and then clustering function here psi, this is same as applying clustering function phi psi at one circle, right? So this one and this one are the same, right? And so somehow, yeah, you will see this. Because from here to here, from here to here, what you get is this S of phi and psi, and here you have S of psi, and then do this. I think something like this. So anyway, this is okay, and then because this term of x omega, and then take pi 1, is certainly a group. So this is invertible. I mean, so phi instead of phi, we can consider phi inverse, right? Phi inverse. Maybe phi is equal to phi t, and then phi inverse may be equal to phi t inverse or something, yeah? And then if we apply them, then actually this is identity. And so for identity, actually, we have only trivial ones. So therefore, in this way, you have a invertible element. So therefore, from here we can say that this Sy is actually invertible. And so this is actually the consequence of this is a group, and this is a homomorphism. Right? So therefore, we have a map from this phi 1 of Ham x omega to this quantum cohomology of x of invertible element, something like this. Okay. So now consider the case of toric manifold x, j, omega, and compact toric scalar manifold. Omega phi, so in general, probably okay, so maybe later I can tell you, but anyway, here actually maybe I can explain something in examples. So I don't know, coupling form maybe Gilman-Lehman standard or something, right? So, but anyway, so now I consider this case. Then certainly the torus group is contained in here. So therefore, you can have this pi 1 of t going to this quantum cohomology of x lambda, something like this. And this one is our n. The lattice n. And yes, lattice n. And lattice n here. Here I have a Gm. And then I wrote as k something like this. And then in dual, actually, we have this m here. and then here's the m, and then this schedule like this. And so this is related to the homology of torus, and there we have Vj. It's a primitive generator of one-dimensional cone in the fan, and then here we have a standard basis element. It goes to this, right? And so here we have this epsilon j. So this epsilon j is somehow related to zj. So I said that this lambda z1 zm, and then linear relation and quantum sterilization relation. And so this z1 to zm somehow related to this. And so if you send it to this, somehow it is actually represented by zj times t to the power something. Okay. So in Fano case. So then here you have element epsilon j going to Vj, but it has a kernel. The kernel is a relation among them, right? Relation among Vj. And this kernel is the source of this quantum sterilization relation in this. So maybe I just explain this a little bit more precisely. So I'm checking some signs. I think the following sign may be okay, but yeah, I think it's okay. So okay, so let's consider S1 action simplex manifold X omega. Okay, and let's suppose that we have a map, the momentum map. Just in this case, it's a momentum map. I don't know, maybe H. And people have different notations, but anyway, so here I take V. V is a sorry. So then I have this real algebra, and then I take a generator V, and then I have a Vx. It's a vector field on this x. And then I of Vx of omega is equal to d of h. This is my this is my convention. Okay. So now from here we should get this p phi over S2. Right? Because it's a Hamiltonian it's a Hamiltonian circle. So this phi is actually this. Phi is now this Hamiltonian circle action. And then this. So this one certainly understood in the following way. So you have this P1. This is Hopf vibration. And then this P phi is nothing but this S3 times X. And then this. Right? So now we try to construct omega phi, but before that maybe we just try to extend omega some way. Okay, so I have this S3 times S1 X here, and over there we have this. So the differential form here is nothing but a so-called basic form here. That means S1 invariant form, and it vanishes on if there is a vector field, yeah, of this circle action. Right? So if I consider just omega here. Yeah. So therefore, I have omega here. So omega is certainly S1 invariant form, but it is not basic, right? So to extend maybe projection to star of omega to a basic form, we add something. So here, maybe I need to understand some sign. And I don't know, this is plus or minus. Let me just write it here. Okay. So alpha is a connection form here. And so somehow we have to add this, or maybe subtract this. So because this action is like this, right? So here I have action like a minus of v of S3, and here I consider Vx. So this is a generator of this diagonal action, and so if I plug in this, then I have only this. So therefore, this one is equal to I of Vx of omega, and then pull back by this. Okay. So I want to kill this by this. And so if I have this, okay, so this term is certainly equal to alpha with I Vx of omega, right? So therefore, if I plug in this to this, the connection form actually gives me -1, right? And then this one, okay? So therefore, if I consider this minus I Vx omega with alpha, certainly I have to also use this projection to star or something. But anyway, you understand this. So then actually this one minus of this one. So therefore it is there, right? Okay. So this is the basic form, right? This is the basic form. But it is not necessarily closed. Just compute the exterior derivative of this. So what is this? I just write like omega. Okay. This is on this product manifold. And then certainly d omega is 0. And then d of I of Vx of omega, this is certainly 0. And then I dump on this. So therefore, I have I of Vx of d alpha. And for Hopf bundle, actually I think d alpha is equal to minus of the pullback of these things, right? Minus of omega downstairs. Maybe I need some constant here, but I just put minus sign there. So therefore, this one is basically minus of is minus of this I Vx omega, and omega is no good. Omega is no good. So this one is maybe something over here. So then I just denote by omega here. Yeah. So omega is actually a scalar form here, right? And then I just put it here over here. So they cancel out. But this is actually the term which we have to think. So let's consider h times capital omega. and then take its texture derivative. And this one is equal to dh with omega. And then, because this one is equal to this, so therefore, if I add them, it is 0, right? So therefore, the extension is omega minus I of dx of omega with alpha, I think plus h of omega. So this one is closed. And this is actually pulled back from downstairs and then multiply function h. So there, it's a S1 invariant function. So this one is actually cannot detect anything on the fiber direction. So if you restrict the fiber, then this is also restricted fiber. You only have this, right? You restrict fiber, then you only have this. So this is a form which extends the simple form of each fiber to the space, so that it is closed in the total space. I think this is okay. Yes. And so, so this is good. But how about the condition for coupling form? So condition for coupling form, somehow the integration along fiber must be trivial. Some power extension along fiber must be trivial. So therefore, we have to pick this h, so-called normalized. Namely, the total integral is equal to 0, right? Then this becomes a coupling form. So you just extend your form using this momentum map, and then if you add constant, then the integration of fiber may not be 0, right? Just changes. So if you have this, and then it is normalized. And then what? So then actually, McDuff and Tolman actually understood the sidereal element of circular action for in certain cases. So their result may be more general, but just restrict myself to the compact Taylor toric manifold. And take the circular action so that the fixed point set contains this dj. Okay. So I have a toric manifold X, and then here I have a polytope. Then here you take a jth facet related to this Lj is equal to 0. And then you have some dj here, which is a full inverse image of this facet. And then you consider circular action in the toric in this torus acting on the toric manifold, so that the weight of the action is just +1. You see, you have normal direction, and then consider the action of weight +1. I think in their paper their conventional moment map is negative to this, and so there are some differences, but So there are different conventions. So therefore, some statement doesn't look like same, but I think this is compatible. So anyways, you have this. And then just run this ideal homomorphism stuff. Okay? So namely, that is a vector Vj. So Vj is an element in this N, right? And then N is one of the interpretation of N is this, right? M is a character and N is a one parameter subgroups. So this is one way to understand this. So therefore, for each facet, this Lj is defined by this Vj minus lambda j here. And so this Vj gives us certain circle action. Right? This is contained in this NR. And NR is also real algebra of this torus. So you just integrate this to this. And so you have this. So here you have a loop, maybe phi of Vj in this term of x omega, right? And then do this. You have a side element. And then the lowest order term is equal to this Poincare dual class of dj times t to the power minus lambda j or something. Sorry. I assume the so now I assume that this polytope. So now P is defined by this affine inequalities, and I just shift the polytope in the dual of real algebra so that the barycenter is the origin. Namely, all the component moment map are normalized. Okay, so that moment map is normalized. Okay. So this is actually same as barycenter is the origin, I think. So we just assume this, and then we can use this sort of computation so that in fiber direction we have this function h appearing here. Okay. Okay, and then this is actually the value of the momentum map. Yes, value of the momentum map there. So I think so. And then, so in general, you have higher order terms. Why you have such a thing? Because it's a fixed point, right? So in this case, you have a P over phi of Vj over S2. So now here, it contains S3 times dj and S1, right? dj is a S1 invariant things, so therefore you have this. And this is nothing but this P1. Sorry, I wrote it P1, right? CP1. So this is CP1 times dj. Just a trivial, kind of flat stuff. And so you can find a lot of constant section here. This constant section is kind of lowest order terms, lowest order contribution to this. And they actually cited some observation by Paul Sider and making, also they put explanation, but anyway, so then they actually explain that this is the lowest order term appearing there. Okay? So Sider element of this guy is equal to this Poincare dual of this dj, t to the minus lambda j, and higher order terms. And if xj omega is Fano, then they also show that this one is equal to 0. So only this term. And then here we have a relation, right? So here, if you have a relation like sigma of aj, bj is equal to 0, then this must give you the same constraint, right? So then S of phi bj and aj, and then take a product, it is equal to identity. And if you just write it, in Fano case, so this is actually something related to this dj. And so therefore, Fano case, then this is a product of j and zj aj, and the t to the minus aj lambda j is equal to 1. And this is nothing but quantum Stanley relational relation. So this is their way of understanding this quantum Stanley relational relation. It actually comes from the relation in this pi 1 of the torus. Okay. I don't know, maybe if I speak a bit more precise, and then maybe story may be more complicated. So therefore, I just stop here for this. So what I want to say is the following. So there is a thing called the sidal homomorphism, and then this one is a mapping from pi 1 of Hamilton diffeomorphism group to the group of invertible of quantum cohomology, and then because our element Vj in the lattice n has linear relations, this linear relation becomes multiplicative relation after taking sidal homomorphism, and this gives you quantum standardization relation here. And so if you just have this is okay for any time. But this one is not equal to this. So there are some other terms. So therefore, the image of this one is not just a Poincare dual of this dj, but maybe other homology classes. And so in non-Fano case, you have other terms. But if you just set this as a kind of generator, and then they satisfy these quantum Stanley relational relations. So if you prefer to have a generator like this, then you have to change relations. But if you're okay to use this as a new generator, and then this one is okay. This quantum Stanley relational type condition is okay. But then there is another thing. So namely, we have two things, right? So Bartlett thing is this lambda of z1 that is zm, and then this linear relation and quantum standardization relation. So quantum standardization, this one holds if you replace this one by this one, so it's okay. But for this one, linear relation is not true, necessarily true, because linear relation is relation among second cohomology classes. So for this Poincare dual of dj, we have linear relation, but now you have higher order terms, and then this relation for this one doesn't really survive for the relation for this one. So therefore, there are two ways. One is you try to keep linear relation. That means you try to keep Z1 to Zm as a geometric things like Poincare of DJ. And then linear relation is okay, but you have to replace quantum Steiner-Lysen relation by other ones. Or if you are satisfied with this, then quantum Steiner-Lysen relation is okay, but linear relation has to be replaced by something else. So you can choose either way. Okay. So I don't know how much I can speak. I have another 1.5 or something. Because I thought that maybe I can speak it more quickly, but not be the case. So today actually I plan to speak some example of bulk deformation in the morning, and then in the afternoon I wanted to discuss this general case, but maybe because as I said, I have to use bulk deformations to understand this. So therefore I need to explain bulk deformations and how it is efficient. That maybe I have to do. Okay. Okay. Maybe that may be better. Is it okay for interpretation of quantum Steiner-Lysen relations?
From this circle action, you can get from the circle action you can get a synthetic quotient.
Yes.
But is this side element related to synthetic quotient?
So simply quotient of
Of the circle. You have a circle.
yes. That actually I don't know. Maybe. So you want to understand this?
So the quantum homology of this is
Yes.
related to the original quantum homology.
Not so clear at this moment. Not clear for me at this moment. Maybe we may discuss later. Yeah. Okay. So maybe I also have some here. I don't know. I don't know. Maybe I just drink just the water.
But the whole Hamiltonian is infinite dimensional.
Yes.
So is it easy to describe the algebra? The algebra is not Hamiltonian vector.
So I mean,
generally constant.
yeah. So actually,
So if the algebra is not clear, then for the whole group, you cannot apply your method to construct a couple. If the algebra is not clear, then you cannot use the method to construct the coupled form.
so then yeah. Maybe we can discuss it in a bit different way. So yes.
moment graph is also clear, then you can.
Yeah, but in fact, in general, the argument is different, and after my talk, actually, I may try to give you something, because there must be some way to.
Well, because the door will lock itself.
Door is locked.
Uh-huh.
Oh, I see. Then we have butchers. Okay. I don't know.
But the loop is not necessarily a subgroup, right?
No, not necessarily. Yeah.
It's looping the subgroup there also.
Yes. But, okay. Okay. No. This, and then I also need something from here. Okay. Okay. Is it okay to start now? Okay. So let me speak on bulk documentation now. So, Actually, at the beginning, we call it infinitesimal deformation. But after some time, we start calling it bulk deformations. So maybe I just remind you the construction in general case. So just a closed-simplex manifold. And then we have a operator QLK beta, which is a map from this. I think I'm writing something from previous talk, I think. So this bracket 2 or bracket 1, maybe you just ignore it. It just means a shifting degrees by 2 or 1. So if I shift degree by 2, that means the K form is the new degree of K form is actually K minus 2. And for this one, actually degree is now degree of difference from minus 1. 2 and 1 is nothing but the dimension of the surface, and this is dimension of the boundary curve. So therefore, this. And so we consider moduli space. Of bordered stable map of genus 0, represent class beta, and K plus 1 boundary mark points and L interior mark points. And so I have a map like this, F1 plus, FL plus, going to the product of X. And then here I have F1, Fk, going to L times L. And then finally it is mapped to X. So you put back the different form here, and then integration of fiber there. So this is actually Pareto deformation, and then it satisfies certain relation, like a infinity relation. But anyway, I just skip this. But toric case, actually we don't really use this. In the toric case, actually we don't really use differential form picture. So actually we consider the following. So I consider cohomology of x and lambda 0. And this is actually, we identify with the T invariant cycles with coefficient in lambda 0 modulo some relation. So here I use differential form and then write everything in differential form. And in our book, we use subcomplex of singular chain complex of X and L and then did something. So in our book, always use singular chain complex. And it is also possible to use differential forms. But here, actually, we use kind of mixture. So the first, this bulk or maybe ambient class, we use just a T invariant cycles and then take this Planck ideal, right? Sorry. Okay. And then take the power, and then we use H1 of LU lambda 0 and tensor K. And this one we use torus invariant differential forms with coefficient in lambda 0. So we use these two things, and then try to map it to this. Sorry. This one is not one, but this. Yes. So we consider this. So, or maybe we just consider another one. This may be better to, in this case, maybe AX, lambda 0, sorry, tensor L, tensor H star of LU. Maybe I should write it first, yeah, and then this. So this is actually a Poincare duals of torus invariant cycles with coefficient in lambda 0. And then you have some relation, and then you get this. Okay. So maybe I explain how it is. So let P1 PPL from this. Okay. And then I consider following moduli space. So moduli space of border stable maps of genus 0 representing class beta, so that L mark points on the boundary, L mark points in the interior, and K plus mark points the boundary, and then like this. And then here I consider this. And then here I have sorry, EV1, EV. Okay. So I have a aberration map at interior mark points, and then here I have chains, torus invariant cycles. So therefore they are included in X, right? So I have a map to L copy of the X by inclusion, and here you have a evaluation map from here to here, and then take the fiber product. So this one, maybe I have to put some topology, but then this one I may define as this M, I don't know, maybe L plus K plus 1, and beta, and then P1, Pn. Something like this. So you can just define. So certainly we need to put some sign here, but just omit this, and then I just denote it by this. And now interior mark points are already used, but boundary mark point remains. So therefore here you have this F1, Fk goes to L, L, and this one goes to L for F0, right? So this is exactly the same picture as before. So without bulk deformation, I don't have any P, and then I have this picture. And then we have operation, Mk, right? Mk operation, L is 0 and nothing here, and then you have this, and then pull back differential forms here, and then put up by this, right? And then this one is actually torus equivariant, and this one also torus equivariant. So therefore, if you start from torus invariant differential form, the pullback is also torus invariant differential form here. And then push out is also torus invariant differential form. So therefore, you may get this sort of maps. Okay? Maybe this map. Okay. So for each P1 to PL, you have this. And then, yeah, as before, using this, we can also show that this H1 of Lu for lambda 0 is contains this MC weak tilde of B of Lu. Sorry, I haven't really defined these things yet. So I have this Q LB, LK beta, but then I define this Q LK as a sum of Q LK beta and then T to the integration of omega over beta. Right? So this is Q LK. And now I want to define this M, K, and this is bulk deformation. And this one is actually the following thing. This is defined to be the sum of 1 over L factorial and Q and LK of, here I take B to the power tensor power of L, and then this. Okay. So I just plug in L many B's here, and then I get the operator on the case tensor product of this guy to here, and then sum them up, right, over L. And this one is well defined or converges in T-addict topology if this B lies in this A x of lambda plus. Because you have L many of them, if it is lambda plus, then you have a lower order exponent. And if you have L many of them, then this exponent actually piling up. So therefore, yeah, this one actually, even though it's a finite infinite sum, but if you have so many B's and then exponent of T actually diverges. So therefore it's okay. But it's not okay for B inside of this A, X, C. So therefore, more precisely, I have to decompose into two parts, maybe B, I don't know, because we have several different notations, and I don't know. Okay. This is a little bit. Okay. So therefore, we define this as follows: MKB in general. So for this is for B in this A x lambda plus, and then we can define this way. And in general, we consider the following. So this is the sum, and this. Okay. So here is the sum over beta, and then here I take exponential of integrating b2 over beta. Yes. And then sum over L factorial, 1 over L factorial, and then rho of d beta, sorry, maybe b0 here, and yes, q of lk beta, and b higher tensor L, and then take t to the particular beta. So this is for general B. And yes. Sorry. This one maybe I have to explain something before this. Yes. Sorry. Maybe I also put some B0 here. So here, this B is the sum of B2 plus B high. And B2, this is actually degree 2 element from here. And this is maybe degree bigger than 2 terms. Yes. And so this is a second cohomology class. And yeah, okay. Maybe better to more precisely. Sorry. Maybe more precisely. Okay. So I just erase this because probably the argument for this may be the next time. So I just erase it. So sorry. Maybe I have to start from here. So first, we consider this space of torus even differential forms, and then I take a basis like f0 and f1 fn, and then fn plus 1 fb. Okay, so this is the basis, and this is actually the whole thing. So it doesn't really do anything because this is somehow nothing, and they are actually torus invariant divisors. So maybe this fj is equal to Poincare dual of this dj, for j is equal to 1 to m, right? So these are in degree 2, and they are actually the torus invariant cycles of dimension less than 2n minus 2. So this is the whole space, and maybe yeah, this is Poincare dual of this, and then maybe Poincare dual of this. So this is degree 0, and this is degree 2, and higher degrees. Okay. So we take such a basis, and sorry, and then this B2 and B high are actually in this A2 of x, and this A of degree bigger than 2 of x. So like this. So divisors actually inverse image of this thing. But I have an interior point U, and then my torus is something like this. And dj is away from this. So therefore, this dj, Poincare idea of dj, has canonically understood as an element in H2 of x. Right? If you think of it as a differential form, and then you just take a Tom class of the normal bundle, and then the support is so small so that away from this LU. So the Tom form vanishes near LU. So therefore, you have this, right? So therefore, we can regard these classes actually element here. So therefore, you can take a pairing with these things. So beta is from here. So therefore, you can take a pairing of them, right? So this is actually a pairing and values in lambda 0. And then take exponential of it. And then I have other terms correspond that is written b high. And then I just use these operators and then do this. And for b0, so b0 is again this b0 is actually from the h1 of LU of C, right? And then we consider associated Floer line bundle, and then consider its monodromy, and then do this. And then just sum them up. So then this one has a definite meaning, right? Definite meaning. So yeah, even though this is actually in complex numbers, this one is a complex number, fixed complex number, and take its exponential, right? Certainly exponential, if we just consider the power series, it is infinite sum, so it doesn't converge. No. If you don't consider topology on complex numbers, then you just have infinite many terms, and then it doesn't really converge in T topology. Certainly it converges in classical topology, but we don't really care classical topology so much. But here actually we somehow use the classical topology, so therefore we just put it here as a definition of these things. So just decompose B into B2 and B high. And then for B high, actually we apply this. And for B2, actually we just put this factor in front. And then from here, we can define this infinity operators. So this is our bulk definition. So for B from this A of x of lambda 0, we have MKB. This is bulk deformed B bulk deformed filtered infinity structures. And then, yeah, probably next time I just talk about the potential function of this. No. I consider the Jacobian ring of the potential function of this, and then try to explain the statement in the beginning of today's talk. But today, I just want to show that this is not just abstract story. I mean, this has some applications. So therefore, yeah, it is actually really new things. I mean, it can give us some new results. Okay. So maybe I just give you some examples. And probably I can explain this example maybe in an hour, and then you may, I hope that you may understand this story is, yeah, something, not just general nonsense. So the example is actually certain 2-point blow up. Certain. So this is actually the example I want to discuss. And maybe before that, maybe this Monday, I discussed a little bit about 1-point blow up. And so before this, maybe recall the case of 1-point blow up of this CP2. Okay. So I have this